All right, so let's talk about ionization energy. As we already defined before, ionization energy is the amount of energy that must be gained by an electron to remove it from its outermost electron shell. So, for example, we have the Bohr model of sodium down here at the bottom of the page. And if we were looking to remove an electron from it, and we're talking about the most loosely held, so usually that is the one that's farthest away, that would be this electron all the way out here. Or in the electron configuration, it would be the one electron on the 3s in the 3s orbital. So the first ionization energy would be the amount of energy needed to remove that electron or to take it out of that orbital. Now this can keep happening, right? There are ionization energies for all of the different electrons. So for example, we can go then, once that one is removed, we can then talk about how much energy would be needed to remove one of the next most loosely held electrons, specifically one of the electrons from this 2p orbital. So we call that the second ionization energy, third, fourth, etc. For all the work that we're going to be doing right now, we're always going to be talking about the first ionization energy and removing the one electron, unless we see otherwise. So in looking at a graph of these ionization energies, we see similar to in the atomic radius graph, there's obviously some repeating patterns here. If we think about ionization energy as being the amount of energy needed to remove the electron, then the thing that would affect that would be how strongly held on those electrons are. So that's going to come back directly to our Coulomb's law, where the force of the attraction is proportional to the two charges, and it's inversely proportional to the distance between those two charges. And again, we're talking about the nucleus for our positive charge, and we're talking about any one of those individual electrons, the one that we are trying to remove. Now, while we have the force of those between the protons and electrons pulling the electrons into the nucleus, if there's more than one electron, or there's different levels of electrons, such as in the case of sodium, we're also going to have the force of the repulsion pushing away between two other electrons. So to balance these two forces, that's going to lead to the trend, just like it did in atomic radius. So if we look at what's happening in the graph, we see that we have this repeating pattern where we start low and end high, start low and high. But overall, it goes down, right, on both cases. In between, there's the increases. Now, not only do we see that general pattern of an overall decrease with these brief moments of going up and down, but even between them, we see that there's a zigzag pattern where it's not one continuous increase from low to high, but we have these little breaks in between, and those breaks are repeating. So there must be a reason for them, right? That repeating pattern there. That same repeating zigzag kind of continues as we go further along the chart. However, then we get to this little part in between before the zigzag that seems to repeat itself as well, right? So something else to look at. And then we end up with these two more flat areas over here. So if we look at specifically what elements are at each of these different regions and where they're at in the periodic table, we can make some explanations and some predictions as to what's going on here. So I went through and I labeled the different points using the CodeOut program, like we did for the last video. And we see that at each of these high points, right, helium, neon, argon, krypton, xenon, mercury, and then radon, all of those points except for mercury there fall into our noble gases. So the highest ionization energy is there at the noble gases, and conversely, we see that all of our lowest points, lithium, sodium, potassium, rubidium, cesium, francium, we're all down there at now our alkali metals. So we see that in general, as we go from left to right, we have an increase in the ionization energy. The amount of energy needed to remove that electron is increasing. If we look then instead at what's going on as we go down the periodic table, like we did for the atomic radius, right? Again, from lithium to sodium to potassium to cesium, we see that ionization energy is decreasing, meaning it gets easier to remove an electron as we go down a group in general. Obviously, there are some exceptions. If we want to explain why that's going on, let's take a look at our models like we had done for atomic radius. We'll take an example of two elements that are in the same group as one another, carbon and fluorine, and see what's going on. For a carbon, if we look at its electron configuration, we have 1s2, 2s2, and 2p2. Whereas for fluorine, we have 1s2, 2s2, 2p5. And we know that both of these, with their proton numbers, would be pulling in on those electrons there. Both of them have two occupied energy levels. So in terms of distance from the nucleus, those electrons are, relatively speaking, the same distance away. We know that their radii are not exactly the same, but number of energy levels is. What is different between them is the number of protons, though. And fluorine has more protons, which means that the force of attraction is going to be higher for fluorine compared to carbon because it has more protons. So since the force of attraction is higher for fluorine, that means that the ionization energy is also going to be higher for fluorine. So we see that it comes down to the nuclear charge, in this case, going from left to right in the periodic table, that is responsible for the increase in the ionization energy. If we look at nitrogen versus phosphorus, nitrogen has 1s2, 2s2, 2p3, whereas phosphorus is 1s2, 2s2, 2p6, 3s2, 3p3. And here we see that nitrogen has electrons across two energy levels, whereas phosphorus has them across three. So since there's a greater distance between the nucleus and those electrons, it means that the force for nitrogen here is going to be higher as those electrons are closer, and the force for phosphorus is going to be lower, leading to a lower ionization energy for phosphorus compared to nitrogen. So as a result, our final comparison is nitrogen is lower than phosphorus, and carbon is lower than fluorine. Now this explains that general downwards trend from the shells and explains the upwards spike from the proton number, but it doesn't explain all of the zigzagging that occurred in between the two. To look at that, we're going to jump ahead really quick. I'm going to look at the example of nitrogen and oxygen, which was this point right here on the graph. To do that, we need to look more closely at what happens with repulsion between two different electrons as we're starting to add these in. Now, nitrogen has 7 electrons, so going into our orbital filling diagrams that we used in the past to really take a look at what's going on here, we can fill this up with its 7 arrows. We do the same thing for oxygen with its 8. Now, even though oxygen has 1 more proton than neon, and we would expect its ionization energy to continue to increase, we see from the graph right there that it doesn't, right? That oxygen dips down a little bit. So for some reason, it is easier to remove 1 electron from oxygen than it is from nitrogen. So if the number of protons is affecting the attractive force in, and they have the same number of shells, then the only thing that could be leading to this effect is if there's a greater repulsion in there that's pushing away against the attraction and reducing the effect of it. So if we look closely at this orbital filling diagram, we see that that 8th electron that we put in for oxygen ends up pairing up with one of the previous electrons in the 2p orbital. That it leads to a greater repulsion between these 2 electrons here, which doesn't exist over here for our nitrogen pair, which means it's going to be easier to remove this 1 electron from the oxygen atom on the right compared to the one on the left, leading to that little dip in the first ionization energy. If we look at the rest of the different zigzags and spikes along there, we should be able to use similar arguments of the number of protons, the orbitals, the pairing, the repulsion, to explain what's going on at any one of those points. And then we're going to end with just one ranking problem like we had done for the atomic radius, where similar to the last one, I'm going to use the number of energy levels for each of these first to figure out what's going on with attraction, because we know that the energy levels and the distance between the protons and the electrons has the greatest effect on the attraction. All right, so let's start by finding the energy levels for each of these, because we know that when there's more energy levels, it's going to reduce the force of attraction, since distance generally has the greatest effect on the attractive force. So using the periodic table or the electron configurations, I know, for example, that fluorine ends in 2p5, argon ends in 3p6, magnesium neutral ends in 3s2, magnesium 1 plus would have one less electron than that, so that would end in 3s1, magnesium 2 plus losing 2 electrons brings me up to 3s0, so really it only has 2 filled energy levels. Oxygen ends in 2p4, and oxygen 2 minus would have 2 more electrons than that previous one, brings it up to 2p6. So in terms of energy levels, I see that fluorine has 2, argon is 3, magnesium 3, magnesium 1 plus 3, magnesium 2 plus is 2, 2 for oxygen, and 2 for oxygen 2 minus. From this, I can start to sort them already into 2 groups, and I see that all of the ones that have 2 energy levels are going to have a higher attractive force, so they're going to have higher ionization energies, and we can kind of split them off to the right side there. So let's take a look at all of these over on this side. For fluorine, magnesium 2 plus, oxygen, and oxygen 2 minus, I can then look to see what else would affect their attractive forces, so I can rank those 4 on their own. And then I'll do the same thing for the ones with 3 energy levels separately. After the energy levels, we know that the next most important thing is the number of protons. So again, looking back at our periodic table, we know that fluorine has 9, magnesium has 12, oxygen has 8, and oxygen 2 minus also has 8 electrons. From this, I see that magnesium 2 plus has the most most protons out of the 4. It's going to have the highest attractive force, meaning that magnesium is going to have to be at the very highest end of my ionization energy ranking here. Fluorine has the next most protons, so the next strongest attraction. And then after that, it's going to come the 2 oxygens. Now, if we remember what effect adding more electrons has on the attractive force and the repulsive force from the last video, we know that when we add more electrons on, they're going to repel each other more, similar to when we were just talking about the paired electron in the oxygen. And when there's more repulsion, it's going to make it then easier to remove an electron. So if it's easier to remove one here, because it has 10 electrons versus oxygen neutrals 8, we know that oxygen 2 minus is then going to have a lower ionization energy because it's easier to remove those electrons. In looking at our atoms that have 3 energy levels, argon has 18 protons, magnesium has 12, and magnesium 1 plus also has 12. So it's for argon, magnesium 1 plus. So out of those 3, I see that argon must have the highest force with its 18 protons. And then after that, I'm going to have the 2 magnesium atom and the ion. Now both of those have the same number of protons, so we're going to look at the number of electrons. I have 12 electrons in the magnesium atom. I only have 11 electrons in the magnesium 1 plus cation, which means that there's going to be more repulsion in the magnesium atom and less repulsion in the magnesium ion. With less repulsion means that the attractive force is going to have a greater effect, and it's going to make it harder to remove one of those more other electrons, making this here my final ranking. Let's take a look at some practice problems, and don't forget I'll be available in office hours if you want to go through any of these a little bit slower or ask any questions about them. Take care.